I'm at the Sandoval and this is Lab 3 Black Hole. Here are the parts to the lab. This lab has two parts and the purposes of these parts are as follows. Part 1 is to determine the mass of a black hole using the correct fundamental physical principles, and Part 2, using the same principles, determine the initial velocity needed for a ship to get as close as possible to the black hole. Fundamental physical principles and models needed for this lab are Newton's second law, parallel and perpendicular components of net force, and universal law of gravitation. Newton's second law allows us to derive the position and velocity update formulas from the equation of net force, which is change in momentum over change in time. It's important to note in this lab that because we are not working on Earth and the force isn't constant between all the objects, the position update formula we are using is going to be using V final as V average. The parallel and perpendicular components of net force also add up to the net force. The parallel component, which is sometimes called P hat, runs parallel to the direction of motion and it can influence an object's speed. N hat, which is the perpendicular component, points towards the center of the kissing circle and influences the direction of an object. The universal law of gravitation allows us to determine the attractive forces exerted on one object by another object. Forces between two objects will always be equal in magnitude, but the direction will differ depending on the system. Because the only force on the star in part 1 is the black hole, this equation can be rearranged to find the mass of the black hole. The details of the experiment took place in 4 steps. The first step is to edit starter glow script code using correct fundamental physical equations for part 1 and part 2. Part 2 was to determine whether by computation or iteration the values required for each experiment instructions. Part 3 was to present the results of each code, and Part 4 is to answer supplemental questions and make conclusions. For Part 1, the initial conditions are as follows. A seed that determines the mass of the black hole, the gravitational constant, star mass, and delta T, which is the time in seconds of an Earth day. For Part 2, I had to input the black hole mass found from Part 1, the gravitational constant, the planet mass, ship mass, delta T, initial time, T max, which is the time to visualize a full orbit, planet speed, planet velocity, and the ship initial velocity. Here's the iteration for part 1 of the lab. The first things I had to calculate were the initial and final momentums, which I calculated using the momentum formula, momentum equals mass times velocity. I next had to calculate the star's change in velocity and change in momentum. To calculate Fnet, I just used dp over dt. Using the formulas discussed earlier, I was able to calculate p hat, the magnitude, and dp dt parallel. Because Fnet is just the perpendicular and parallel components added, to find the perpendicular component, all I had to do was subtract the parallel component from Fnet. In each iteration, the mass of the black hole was calculated using a rearranged formula of the universal law of gravitation. I then added a variable called mass total, which increases by the mass of the black hole for each iteration. I also added a variable called counter, which increased by 1 for each iteration. At the end of the while loop, I divided the mass total by the counter in order to get an average for the mass of the black hole. Here are the results of computational model 1. So the Fnet parallel, and Fnet perpendicular were calculated as shown, and the mass average of the black hole was 1.86, followed by some amount of decimals, E34. The errors were larger when closer to the black hole because there is greater gravitational force the closer you are to an object. And the arrows point in the direction of p hat and n hat. The n hat arrow always points towards the center of the kissing circle, which is the orbit, and p hat always points in the direction of motion. The iteration code consists of 2 repetitions of the universal gravitational formula and velocity and position update formulas. Because there was both a star and a ship, I had to calculate the net force on both these objects. This was accomplished using the universal law of gravitation. In both of these chunks of code, I found the position of the system minus the source, then the position unit vector, and then the force. Finally, the force using the gravitational constant, the masses of each object, the position vector, and the unit vector. Once I had both of these net forces, I used each of them to find the velocity and position updates for the planet and the ship. These are the results of the computational model 2. The ship's initial velocity, which is negative 4.1 e to the 7, 0.24 times e to the 7, 0 meters per second, was calculated through trial and error. Here's some discussions of the different parts. For part 1, the gravitational force of the black hole draws the star into an elliptical orbit. As shown by the size of the arrows, the magnitude of the gravitational force of the orbit increases as the star nears the black hole. In each iteration of the code, the mass of the black hole was calculated, and an average of all these values was calculated at the end of the code, providing an average of the mass of the black hole. Possible sources of error for part 1 include rounding errors within iterations of code and human error in inputting formulas and data. For part 2, the gravitational force of the black hole draws the star into an elliptical orbit again. The ship is also drawn into this orbit, that is, if its initial velocity is not to a certain magnitude. Possible sources of error for part 2 include rounding errors, again, human error in inputting data, and the initial velocity could be optimized. Now to address some important questions. The first question asks how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. Based on the construction of the formulas, it can be said that the components of the net force are the same as the rate of change of momentum, The only difference lies within the calculations, as finding the net force in part 1 of the lab requires one to know the masses of both the black hole and the star. The rate of change of momentum can be found using position, time, and velocity, though. The next question wanted to know, what if the ship were to enter the orbit around the black hole? For this to be possible, the initial velocity would be negative 0.8 times e to the 7, 1.12 times e to the 7, 0 meters per second. Like the initial velocity from earlier, this velocity could be improved and optimized. However, the value I presented is sufficient for the ship to enter orbit.